In this video, I would like to prove the fundamental theorem of calculus. When you get into your higher level math courses, most of the course will be proving things. So if you're interested in mathematics, it would be good for you to study this. So let's first of all write what is the fundamental theorem of calculus. If little f is continuous, a continuous function on an interval I, and a is some element of I, a is some real number that is inside the interval, and capital F of x is equal to the integral from a to x of little f of t dt, the fundamental theorem says then that capital F prime of x is little f of x. And we would like to prove this. So when you prove something in mathematics, you usually have to go back to the definition. What is capital F prime of x? So we go back, let's call this the proof, and we'll go back and to Calc 1 and say, well, what is f prime of x? What's the definition? It's a limit. The limit as h approaches 0 of capital F of x plus h minus capital F of x all over h. And you know that in finding, for example, the derivative of the sine function and the cosine function and secant, you actually had to compute these limits in order to find what the derivatives were. Well, we have to, in the same way, we have to show that this limit is indeed little f of x to prove the fundamental theorem of calculus. So let's write that again. Let's write what we have to do. We must prove or show that the limit as h approaches 0 of capital F of x plus h minus capital F of x all over h is little f of x, and then we'll be done. So let's draw a picture and look at exactly what this quantity f of x plus h minus capital F of x is. Let's see, we've got little f, maybe looking like this, y equals f of t, little f of t. And we have, here I'll get another color, we have maybe a is right here, and let's just pick x anywhere, pick it right here. And for the sake of the drawing, I'll assume that h is a positive number, so that I'll put x plus h to the right of x. The proof would go just as well if I put it on the left-hand side. Okay, so let's shade in these areas. The integral from capital F of x plus h is the integral from a to x plus h. So capital F of x plus h is that area right there, minus capital F of x. Well, capital F of x is that area there. So we see, I'll shade it in red, that capital F of x plus h minus capital F of x is this red region that I drew under the curve. In fact, we can say that capital F of x plus h minus capital F of x is really the integral from x to x plus h of little f of t dt. You can see that on the picture. Now imagine h really, really, really small. Then f of the y value here at f of x and the y value here at f of x plus h will be almost the same. for all practical purposes, they'll be the same. In other words, this pink area would be a rectangle. As h approaches 0, this approaches x, and this becomes very, very close to a skinny, skinny little rectangle. And so the integral from x to x plus h, we could say, is approximately a little rectangle of width h and height f of x. Remember, we're imagining that x is not changing. H is going to 0. So the height of that little skinny rectangle is about f of x. And so it's approximately h times f of x when h is very, very small. So this isn't really a proof, but we're seeing what we need to do. You can see then that f of x plus h minus f of x, the integral, divided by h, is very, very close, as h gets small, very, very close to this divided by h, which is little f of x. So this makes sense to us. As h approaches 0, we can see that this difference quotient does indeed approach f of x, but we have to be able to write a more rigorous proof than what we just did looking at the picture. So this is y equals f of t. I just recopied the picture here. Okay, so the red region there that is almost a rectangle, you can see that the function y equals f of t is continuous on our entire interval capital I, so f is certainly continuous on the little closed interval x plus h for any given h. That means that f attains a maximum value m, capital M, and a minimum little m on the interval x plus h. You remember that theorem? It was the extreme value theorem. Any function continuous on a closed interval has a maximum and minimum value on that interval. So we can take, we can take this difference f of x plus h minus capital F of x, and we can say that that difference is that difference f of x plus h minus f of x is less, that's the red area there, is less than or equal to capital M times h, and is greater than or equal to little m times h. Capital in here where you see it looks like it's increasing, well then m would be right here, and we're talking about the big rectangle, m times h, m by h, and then you have a little rectangle, little m by h, and the red area is in between them. So this implies, if we divide through by h, which is a positive number, m is less than or equal to capital F of x plus h minus capital F of x all over h is less than or equal to capital M. So this is what we know, and certainly if as h approaches 0, the width of that little interval approaches 0, little m and big M both approach exactly the same thing. As h approaches 0, big M approaches f of x. And as h approaches 0, as the width of the interval becomes close to 0, the minimum value is also approaching f of x. So we have proven then that the limit, by the squeeze theorem, I'll call it SQT, by the squeeze theorem, therefore, the limit as h approaches 0 of f of x plus h minus f of x all over h is indeed equal to f of x. You might have to look up the squeeze theorem. You had that in Calc 1. If you have a function squeezed in between two others, and the limit of the left-hand side is going to f of x, and the limit of the right-hand side is going to f of x, then certainly what is trapped in between also has the same limit. So we have proven what we needed, and we can conclude, therefore, those three dots mean therefore, f prime of x is little f of x.